Okay, and then the last bit of information is integration. Okay. What does integration tell you?
Oh, it's the ratio of peaks.
It's the ratio of the signals. Yeah, exactly. Okay. So let's say I've got this system. We're gonna do an example by looking at your products, and I'll leave it for that to do an example rather than beat this to death here. So it's a ratio relative to number of ages pausing the signal. Okay? And just like where else have we seen it? Integration in gas chromatograph spectrum. Okay? Gives you an idea. It's the same usage of the word integration that you do in calculus, which is the area under the curve. So what the machine does is actually looks at a signal, checks out all the area under all the spikes of the signal, and adds it up. If you've got two different signals, if you had this signal and this signal, okay, and they add up to the same number, and that number might not be 1, 2, or 3, which is the way we think of protons. It might be 60 and 59, which we would count as the same. Okay? Then we know that the same number of protons are causing that signal. Does that make some sense? Make a little bit more sense when we start to do it. Questions so far? All right. Let's look at what we expect for our okay. All right, so let's take a look at what we would expect for okay. All right. How many different proton types are on that molecule?
4, 5. Oh. Different protons.
Yeah, it's 4. It's 4. Yeah. Okay, so there, and there. Okay? There's no carbons that have the same type as a proton. In part because this is asymmetrical. Okay? So A, B, C. All right. Now, it's very helpful, especially when you're trying to confirm. Okay, I made this. It's very helpful to try and anticipate what that NMR should look like. Okay? 0, 1, 2, 3, 4, 5, 6, 7. Okay. The signal for D, where would we expect that to come?
Closer towards 0.
Yeah, right. It's a methyl group. Yes, there's an electronegative thing on the chain, but electronegativity effects fall off real quickly. So A feels the electronegativity. B kind of feels something, but not much. C don't really feel that much, not hardly at all. Okay, the inductive effect, the effect through sigma bonds, falls off quickly. All right, so we expect D, and then what do we expect the multiplicity for D to be?
3.
A triplet, exactly. Okay. So, very good. All right. That's what we expect there. Okay. All right, C. Where would we think C would be? It's a CH2. It's probably just going to be like in this range, right? Really doesn't feel much of the bromine, so not too much going on. All right. So, and what would we expect the multiplicity of C to be? Yeah, sextet. It's got 5 neighbors, 2 here, 3 here. Okay. They're different neighbors, and sometimes different neighbors has a different effect. Not today. They have the same effect, so we can just use the simple m plus 1. All right. So sextet, it'll be like right here. That, I think I want this down here. So that's C. All right. B. Quintet. Now B is probably starting to feel bromine. It's gotten closer, yeah? So should I send it upfield or downfield? Downfield, more that way, yeah. Okay, so, what do we say? Quintet. Okay. All right, and then A. Where would we expect A to be? Farther downfield, somewhere between 3 and 5. Okay. Would we expect it to be more on the 5-ish or more on the 3-ish? Yeah, exactly. A little bit more on the 3-ish. A little bit more upfield because it's the second least electronegative halogen. And what would we expect the multiplicity of A to be? Triplet. Yeah, 2 neighbors. Yeah, I can really see that you guys have got that one. Okay. Okay. Perfect. Now, I drew the A triplet much smaller, or not much smaller, a fair amount smaller than I did the D triplet. Okay? And it's not just because of my crappy artistic skills. It was on purpose. Why did I do that? Why did I make it small?
There's not a lot of it.
What's that?
Because there's not a lot.
Ain't wrong. Big enough to be right. Why did I draw it smaller than D?
Just because you could.
Because there are 3 protons causing D. There's only 2 protons causing A. That's integration. Does that make sense? It's the number of protons causing it. Okay. Integration is often it makes this weird little line above, but then it'll give you a number down here too. So it'll give you a line like that. Give you a line like that. Okay. C is 2 H's. This is 3 H's. So this should be about 2/3 the height of that. Same with that. And same with that. Okay. And then it'll spit out numbers down here. All right. And so this could be 89. Let's say. And then this could be 29. Oh no, maybe 29. could be 51, this could be 49, and this could be 52. Okay? What I'm trying to convey by awkwardly making up these numbers here is that these integrations aren't perfect. They're not dead on. Okay? So don't divide this into that and go, wait, that's not exactly, you know, 2/3. That was 0.643. Okay, that's not 2/3. 2/3 is 0.666. Okay, it's not that close. All right. These numbers can be a little bit annoying if you're really using this to solve an NMR problem. So what we can do a lot of the time is calibrate these. We can tell the NMR, you know, 52 protons on a carbon doesn't make any sense to us. So what we can do is we can tell the machine, hey machine, you know, I'm kind of unsure about some of these signals, but I know, and very frequently, anything that's sort of like round 1 is a methyl. So you can tell the machine, hey machine, set that to 3. I'm pretty confident that's a methyl. So get rid of your 89 and set that to 3. The machine will go, okay. And then it will come here and it will fix these. Now it's easier to count. They might be a little bit funky, 1.9 and 2.1 instead of 2s. Okay, that's fine. You go close enough. 2, 2, 2. You're looking for a close relative ratio. Does that make some sense? Okay. Running out of color. Rainbow. Okay. This is going to be mixed in here with this. All right. And let's say that this is D prime and C prime and B prime and A prime. Okay? We could go through and have that whole same discussion. We expect all these signals to be the same, right? Okay? And if these ratios hold, okay, they're in the same molecule. But if you have 2 molecules in your sample, okay, your integrations are going to be quite different depending on how much you have. Okay? Let's look at just A prime. We would expect A prime to be a triplet again, right? For the same reasons it was with A. We would expect it to be in this range. We expect it to be upfield or downfield of A. Downfield, exactly, because chlorine is more electronegative. And that's indeed the case. I'm not sure. I just threw this here. You know, don't sue me if it ends up being from it all. Okay. And so that's A prime. Then this has some sort of integration here. Okay. It'll spit out another number for this guy. Maybe it's 13 or something. I don't know. Now you can use these 2 numbers. Okay. And we can use that as a ratio of how much of these are in solution. It's important that I picked 2 CH2s, okay? You got to do some extra math if you decide, I'm going to pick a CH2 on this molecule and compare it to a CH3 on that molecule. Then you need to do some extra math. But when you're comparing the quantities of 2 different compounds in solution, it's helpful to pick, all right, let's compare methyls to methyls, or CH2s to CH2s, or CHs to CHs. Does that make sense, guys? So this is your goal today, to get this spectrum. You ought to have 2 triplets kind of around in this range, okay? And those will give you your ratios. You know that the one that's farther downfield is going to be due to the 1-chlorobutane. Okay, butyl chloride. Make sense? All right, let's do one more real quick. How many different types of protons on that guy? 4. yeah, there's 4 different types. Okay. Good job, whoever said that. Didn't forget that there's an H right there. All right, so let's label those dudes. Should I use A, B, C, D again, or is that confusing with that?
No.
Okay, good. Good answer. That's what I wanted to hear. Okay. All right, beautiful. A, where do we expect A to live? Yeah. And A, you know, could feel a little bit of the burn line. Maybe it'll be just a hair past 1, not much. Okay. Multiplicity of A? Triplet. Integration is going to be ultimately the integration ratio. He's going to count for how many protons? Three. Yes. Okay, B. What would we expect the multiplicity, or where would we expect B? We'd expect B to be somewhere between, and you know what I like? This is really too far away, and it's kind of in my way of my tiny spectrum. So I'm going to move him. He ain't going to be down there. He's probably. All right. B, we would expect to be a little bit farther down here, right? And the multiplicity of B? Quintet. Yeah, exactly. It's got 4 neighbors, and plus 1 is 5. So quintet. All right. And then C. C, down here, right? We would expect C to be somewhere between 3 and 4. And what would the multiplicity of C be?
Sextet.
Sextet, yeah, exactly. So let's put them right on. Okay. I really made that too big. Discussion here, not that you care. I'm a little bit OCD. Okay. All right.
Shouldn't that be C?
Oh yeah. Okay. C. Okay. All right. And then D is going to be what? A doublet. Yeah, exactly. And he will be a little bit farther downfield because he does feel the bromine, but a tiny bit. It's the bromine. Okay, that's D. Awesome. Okay. Integration for this triplet is going to be 3-ish. Okay. D is going to be 3-ish. All right. B is going to be 2-ish. And this is going to be what-ish?
1-ish.
1-ish. So I should make it 1/3 the size of these guys, to the best of my artistic abilities. Okay. All right. Beautiful. Now. So we also have, okay, it's going to have all the same signals, right? A prime, B prime, C prime, D prime, okay. And where would we expect C prime to be versus C? Downfield or upfield? Downfield. But this is where my asterisk comes into play. Okay? For some odd reason, with these two molecules, it's the reverse. Okay? The chloride is upfield. Dr. Organ he's an expert on NMR, and he's given me some explanation to it that seemed possible.
We'll just take your word for it.
Sounds like a plan. All right. Oh, maybe it's green. And it should be like that. And it will have some integration. And now these two, make sure you've assigned them correctly. I just told you which one's which. And this gives you, you can use the integration to give you the ratio of the two compounds in solution. All right? We good? Right. Okay. Lastly, we're going to look at the T-butyl. And you already know GC. You're GC experts. Okay. We're going to be looking for a mixture. T-butyl bromide, T-butyl chloride. Okay. Just for kicks, what did we expect that ratio to be near? 50-50. Why? Bromides are better nucleophile than chloride. Why, Hero?
Because of the mechanism. It doesn't care about the
Good job.
Perfect.
I don't know which mechanism that is, but
We expect this to be an SN1 mechanism. SN1 mechanism don't care what kind of nucleophile you are. By the time it makes a carbonyl, it will react with anything. Okay? All right. We will analyze this using gas chromatography. Okay? Remember, chromatograph is now based on time as your x-axis. And so, chromatograph, out. If it really is 50-50, we'd like to see two bumps near the same side. You know, if it ends up being just off or something, you know, 47 to 53, that's probably close enough. Okay? Question for you. Which one do we expect to come off the column first, i.e. have the quicker retention time?
the less electronegative one.
Electronegativity here.
Is CL going to be faster?
What?
Because it's smaller.
Because it's smaller. Yeah, exactly. This is based on boiling point. And so we got to look at those two guys and go, which one would we anticipate having the lower boiling point? The one with the lower boiling point is going to come off the column faster. Okay? And with the halogens, it's almost the opposite of what you suggested, Michaela, that with alkyl halides, the boiling point trend goes against electronegativity. In spite of the fact that you have a bigger dipole here than you do here, bromine is like one of those bouncy balls you sit on. Chlorine is a softball. Okay. Fluoride is marble. All right. And so dispersion forces play a much bigger part in the difference of these two. Okay. So we would expect your alkyl chloride to come off, or your alkyl chloride. Does that make sense, folks? Okay. In terms of preparing our samples, we are going, and I had them reprint out the handouts. We are going to prepare your GCMS samples just like we did for cyclohexenes. Remember, we put in 90 microliters of acetone, and then we put in your 10 microliters of your sample. Yeah, and then we added, last time we added chloroform, this time we're adding dichloromethane. Okay, and then we run it through that column. Does everybody remember that? Okay, and I got the handout, I had them reprinted for you. Now, I don't have a handout for the NMR preparation, but it couldn't be more simple. Okay, all right. This is an NMR tube where your sample goes. What you're going to do is you're going to stick this guy down into your sample. And by capillary action, it'll pick up a tiny bit. If you could see it, you can NMR it. Okay, so don't worry about oh, I didn't make so much. That's all good. And then it goes into the NMR tube like that. Okay? And then we want to use every once in a while I have people who just put this rubber thing into a solvent. Don't do that. NMR solvent is fairly expensive. You have to make sure that your NMR solvent doesn't have any protons on it, or you'll just take an NMR of a giant redwood tree of your solvent, and your actual sample won't be there. So you got to do something that in that range is invisible to NMR, like deuterium. Okay. All right. So anywho, we're using deuterated chloroform, okay, which right behind Aaron, right back there, and this guy is 1 mil. We're going to pick up 0.8 mLs. Okay. And then I'm going to put it in this pipette. And this pipette is in the NMR tube. And then that washes it out of this pipette into the NMR tube. And then I put an NMR cap on it, which is over there, those red caps, little itty bitty caps, and I'm done. That was it. Does that make sense? Okay. Oh, I'm not done. I lied. Okay, folks at home. Yeah, some special effects. Yeah. Whoa, you run out of cord. Okay. Am I on the film? Yeah. Okay.
Yes.
All right. After you've made that sample, I don't know why, but if you do 0.8, it should come out okay. But sometimes it doesn't come out okay. There's a little scale here that I made. You want to hold this guy up to it, put your NMR tube down to the bottom, and you want the top of your solvent to be in the green zone. Okay? You don't want it to be above the green zone, you don't want it to be below the green zone. If it's below the green zone, we've got to add a little bit of just plain old deuterated chloroform. If it's above the green zone, then we got to carefully dump some out. So all that makes sense, guys. And then we got to clean out our desks. We got to get ready for finals, for weeks and weeks of relaxation, recuperation.
Gotta be ready for,
Yeah, 6
okay.